Good morning, all my MHF4U students. I'm not with you today, but I'm here even if I'm not there. So you've got this video to watch on rational functions of the form f at x equals ax plus b over cx plus d. Good luck. To get started, head to student.desmos.com and type in S5 3Q4 and try the activity, please. Hopefully when you completed the Desmos activity, you ended up with cards that look like this. So how do we get these? Well, looking at the graph, this first graph, we can see that the blue lines, so the vertical asymptote, is definitely at a half. And we can see that the horizontal asymptote is also at a half, at y equals a half. Now, the connection we need to be able to make, though, is how do we get those asymptotes from this equation? Well, if you recall, we can find the vertical asymptote by setting the equation, the denominator to 0. So I'm going to set 2x minus 1 equal to 0. So then x equals 1 over 2. That is how you get the vertical asymptote. The horizontal asymptote, though, also 1/2 in this case, right here, is a little bit different. What we want to consider is the coefficients of our x terms here. So the coefficient on the top is a 1, even though we can't see it. In the previous section, we considered what would happen as x went to infinity. But if we look at this equation as x goes to infinity, then we'll find that both the top goes to infinity and the bottom goes to infinity. So it's not very helpful. So what we're going to do instead is we're going to divide everything by x. So then so for the horizontal asymptote, we're going to divide each term in the f at x by x. So x over x, and then 2x over x minus 1 over x. On the top I end up with a 1, and on the bottom I end up with a 2 minus 1 over x. And as x gets very, very big, like goes to infinity, then this term will go to 0. And then our horizontal asymptote is what's left. So 2 minus 0 on the bottom and a 1 on the top. So our horizontal asymptote will be 1 over 2. Okay, moving on to the second one here. I'm going to make it big. You can see the second one. We can see that the the vertical asymptote is x equals 1. So I'm just going to actually get a pointer here. So this is x equals 1. And the horizontal asymptote is y equals 1. So this is in fact true. But then how did that come from here? Well, again, the vertical asymptote, like before, we're going to get from looking at the denominator. So when x minus 1 equals 0, this whole function becomes undefined. So then when x equals 1, that's a problem. That's when it's 0. So that's why we're going to get the vertical asymptote of x equals 1. Now, in order to do the horizontal asymptote for this one, we need to consider what happens as x gets very, very large. And when we see that as x gets very, very large, this goes to infinity, as does this. And so that's not very helpful. So what I'm going to do instead is I'm going to divide every single x term, or every single term, by x. And what I end up with is 1 on the top and 1 minus 1 over x on the bottom. So this is an equivalent comparison. So as we look at this one, as x gets very large, this term goes to 0, and I'm left with 1 over 1. So the horizontal asymptote is 1. Thank you. You figure out the other two. Today we're looking at functions defined by this equation, ax plus b over cx plus d. We're going to be able to describe key features of those functions and compare them to other rational functions. This is one particular function, x over x minus 2. We know that the vertical asymptote happens when the denominator equals 0, because we cannot divide by 0. So when x minus 2 equals 0, we get x equals 2. So our vertical asymptote is x equals 2. The horizontal asymptote happens as x gets very large. What happens to y? So looking over here, again, as x gets large, infinity on top and infinity on bottom, that's hard to compare. So what we're going to do is we're going to divide every single term, top and bottom, by x. And then I get 1 over 1 minus 2 over x. And now we know that as this x gets very, very large, this term goes to 0, and I'm left with 1 over 1. So the horizontal asymptote is y equals 1. The intercepts happen when x equals 0. What is y? So that's going to be the y-intercept. So if x equals 0, we get 0. So the y-intercept is 0, 0. Now, when y equals 0, find x. So we get 0 equals x over x minus 2. And then x equals 0. So also 0, 0 for the x-intercept. Now, continuing from the previous page, we can see that we've verified that our horizontal asymptote is y equals 1, and our vertical asymptote is x equals 2, just as we had said on the previous page. Also, we're confirming that our x-intercept is 0, 0, as is our y-intercept. To consider our behavior around the asymptote, we're looking at the asymptote of x equals 2, the vertical asymptote. And we're going to look at numbers coming close to 2, but before 2, so in the left part of the graph. So we're going to look at numbers leading up to the x equals 2. So if we try 1.9, and if we put that in, we get f of 1.9 equals 1.9 over 1.9 minus 2. So on the top we have 1.9, and on the bottom we have 1.9 minus 2, which gives us negative 0.1, which equals 19, or negative 19 rather. So we know as we're approaching the asymptote from the left-hand side, so from over here, as we get very close to it, it becomes negative. And if we try 1.99, we're going to get even more negative, but we're never going to cross that x equals 2 line. Alright, let's look at it from the other side. I'm going to try f at 2.1 and see what happens. So I plug the 2.1 in on the top, and 2.1 minus 2 on the bottom. So evaluating f at 2.1, I end up with 21. So that's a positive number. So I know as I'm coming from the right-hand side on my graph, f close to 2 but not at 2 is going to be 21 or positive. The end behavior talks about what happens as x gets goes towards negative infinity, and as x goes towards positive infinity. Look at x as x goes to negative infinity, so we're going this way on the graph, and we can see from the graph that it gets closer, y gets closer and closer to 1. Using the equation, we can write, we could use a very large number if you like, let's say 1,000. So f at 1,000 equals 1,000 over, negative 1,000. I should make that all negatives. Negative 1,000 minus 2 equals negative 1,000 over negative 1,002. Now you can see that that number is fairly close to 1. And of course, the larger we get, the closer it gets to 1. And that's why we have a horizontal asymptote at y equals 1. Similarly, we can do the same thing for as x goes to positive infinity. So we can use a very large number, let's say 1,000. So on the top we have 1,000. On the bottom we have 1,000 minus 2. So we end up with 1,000 over 998, which is, again, very close to 1. And you can see over here that as we continue towards infinity, this is going towards 1 and not going to cross it. So that's the end behavior for this graph. Finally, for the vertical asymptote, we're going to set the denominator equal to 0 and solve for x. For the horizontal asymptote, we're going to divide each term in the numerator and denominator by x and investigate the behavior as x goes to positive or negative infinity. Good luck with your homework. For your homework, look for this document in the hub.